Today we're going to focus on forces and the energy of matter. We're going to look at all the different types of energy. First, you need to know that a force is a push or a pull. When something basically gives off or exerts a force on an object, that object will push back, will exert that force back. So all forces act in pairs. There's contact forces and then there's field forces. Contact forces, this is when an object is touched. So here's the word contact, meaning touched. And then you have field forces. This is basically, this is a force that even when the object isn't touching, it's giving off this force. So a contact force, okay, would be if you're pushing something or pulling something. But a field force is a force given off by maybe a magnet, a magnetic force, or maybe gravity or electricity. Gravity is basically it is a force that's going to act on every particle. On different planets, we have different levels of a gravitational force. And so basically, we're going to be talking about mass versus weight. Weight is actually mass times gravity. So if the mass of an object is 10 grams, when you talk about the weight, you're going to multiply the 5 grams times the planet's gravity. So we would multiply it by Earth's gravity to get the weight. Weight is measured in newtons, which is different from mass measuring in grams. Now the thing is, if you go online and you look up the mass of an object or the weight of an object, a lot of times they say it's the same thing. They may say both of them are measured in grams. That's incorrect. Weight is different from mass. Weight is the mass times the gravity. So make sure you know weight is mass times gravity, while mass is just the basic measurement of how much matter it contains. Talking about the number of atoms measured in grams or kilograms. So if we look at planets, you can actually see if your mass on Earth is 150 pounds, then your weight is 666 newtons. But if you go on the moon, there's less gravity. So if your mass is 150 pounds, your weight would be 109 newtons. So a little more than 500 newtons less. Now, if you go to Jupiter, however, the gravity is extreme. So even though you have 150 pounds, okay, 68 kilograms, because that's what we focus on, mass, usually with grams, 68 kilograms, your weight, your newtons, would be 1,700 newtons. So very, very strong. Gravity is so strong you would not be able to kind of pull yourself up. So very strong. Okay, so you can see the difference between the moon. The astronauts could walk on, they could kind of jump, float a little bit, but very different from Jupiter. Okay, energy. Energy is the ability to do work. Work is a force that acts on the object, and the key word here is moving through a distance. So if I move the object, so if I do a push or a pull, and I'm moving the object, not just the push or pull, but moving it over a distance, that is work. So I'm combining force over a distance. Okay, if I pull something 5 meters, well, that is work. If I push something 6 kilometers, okay, that is work. And that's a long ways. When you lift something higher or lower, you're doing work for the object. Doing work for an object changes its energy, and this is where it's going to tie in with kinetic and potential energy. You should have learned in elementary school. Kinetic energy is the energy of something that's in motion, while potential energy is stored energy. So if I'm holding the object, that is potential energy. When I let go of the object, it starts to fall. That is kinetic energy. It's the object in motion. And we abbreviate kinetic energy with KE, potential energy with PE. And both of those are examples of mechanical energy, which basically results in the keyword mechanical, physical, a physical force. On the left, I'm holding the microphone. That is potential energy. On the right, I drop the mic. That is kinetic. Okay, another type of energy is thermal energy. We talked about heat entering the ice cube to melt it, heat entering the gas of the air to condensate the water to turn it from gas to liquid. So heat is the flow of thermal energy. What is thermal energy? It's the sum total. It's the total of all energy by the movement or the random movement of the atoms. So basically, if heat, which is the flow, if heat is entering an object, most likely it's going to be hotter. If heat is leaving an object, that will become colder. So you're moving from a hot to cold place, the transfer of heat. Now, temperature and heat have similar concepts, but temperature is different. Temperature is focusing more on how fast the objects are moving, the particles are moving. If we look at heat, it's the movement of thermal energy, while temperature is basically identifying is the random movement of objects increasing or decreasing? Are they going faster or lower? I do need you to be aware of the Fahrenheit scale, which is what we're using in the United States. In Europe and Asia, they use the Celsius scale. One thing that I always remembered was that my body temperature is 98.6 degrees Fahrenheit. It's also 37 Celsius. So when I was dealing with students in Korea, the focus was checking body temperature at 37 degrees Celsius. So if you can kind of create that pattern in your mind that 37 degrees Celsius is similar to 98.6, okay, that is going to help you kind of estimate that. I know in elementary school we had the calculations. I'm not going to give you those calculations now. Look over the basic characteristics of freezing, boiling, room temperature, and you kind of get an idea there. And we will be using this probably when we get to weather and climate. So we'll see this again. And we'll get into more detail about that, specifically about the calculations when we get to weather. Sound energy. Now we're going to see this chart when we go into ocean water, when we talk about waves with ocean water. So you will see wavelength, crest. Amplitude is another name for wave height. The crest is the top of the wave. The trough or trough is at the bottom. Now, electrical energy, again, is dealing with the force, the ability to do work of moving an object through a distance. And by doing this, we're able to focus on the electrical charges of the atom. It's focusing on the positive charges, the negative charges. The battery is moving electricity from the anode to the cathode. So basically we have work, it's moving through a distance to the light bulb around that circuit. So the anode is the negative end, the cathode is the positive end. We saw this when we saw Crookes tube. Remember, we added the electricity, it moved from the anode to the cathode, so those little charges were moving through the glass tube apparatus from one end of the circuit to the other, and they kind of kept going straight as they hit that little cross that made the shadow in the glass tube apparatus. Make sure you know that opposite charges attract. We saw that with the glass tube apparatus as well. Positive is always attracted to negative. Like charges repel, so positive and positive will repel, go away from each other. Negative and negative will also repel. Magnetic energy, if you have the understanding of the battery, the circuit, you're going to understand this. You have your poles, your north and south pole. The magnet gives off a field force. We said we're not touching that, but basically this energy results in the motion or movement of the electrical charges. Okay. Chemical energy, we can see this in a battery. We can see bonds are being broken to form a new substance through the process of a chemical change. This is seen in the process of burning fossil fuels such as coal, oil, and natural gas. Battery is a potential chemical energy form because it's storing it. Once we hook it into the circuit, then we have the kinetic, which is the electrical energy, okay, moving from one place to another. Light energy. So basically anything that gives off light produces light energy. Now remember, light energy isn't just visible light, not just what you see. Different things give off different forms of light energy, or this different wavelength of energy. So we have ultraviolet light, X-rays, gamma rays, and then on the other end of the spectrum, infrared, microwave, and radio waves. Now you can see when we move to the right, okay, ultraviolet, X-ray, and gamma, it's getting smaller. Okay, you can see nanometers. Okay, nanometer is very, very tiny, so it's getting tinier and tinier. If we go to the left of visible light, 1 meter you can see is larger than 1 millimeter. So the size impacts perhaps the color of the wavelength and or the colors of visible light. Okay, we're going to end with nuclear energy. This is when an atom is split, energy is released. This can happen in nature by the breakdown of an element if something's radioactive, or it can happen in a laboratory being split, the atom bomb. But even in nuclear power plants, the atom is being split to produce a great amount of energy, but at what cost?